Hello everyone, welcome back from spring break. Hope everyone had an enjoyable spring break, even with the shelter-in-place protocol. But besides that, it's time to get back into the swing of things. So we're going to go ahead and continue on with our lectures, and today's video is going to be talking about two things: the rational zero test and the intermediate value theorem. Those are going to be our two topics of discussion today. So why don't we go ahead and get right on into it. Okay, so the rational zero test. Here it is. Let's go ahead and just read on through it. If f of x is a polynomial function, so for example, we have our generic polynomial function, a sub n times x to the n plus blah 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 plus a sub 1 times x plus a naught. So we have some polynomial function where the a's are integer coefficients. So each one of these a's are integers. Alright, so 1, 2, 3, 4, 5, yada yada yada. Then all rational zeros of f have this following form. The rational zero will equal a factor of a naught, so a factor of that coefficient term, divided by a factor of a n, divided by a factor of that leading coefficient term. And we'll call this p over q. This is how we'll simplify our notation down. So factors of a naught are p, factors of a n are q, and we're going to make the claim that p over q is as simplified as possible. Okay, so there's a lot going on in this test, just describing the test. There's a lot going on here. And I've highlighted or underlined in blue the important words from this. There's another one I forgot. All the important phrases from this test. So as you can see, just writing the test took up a whole board, and so there's a lot going on here. So let's go ahead and just talk about and dissect this test. But in order to do that, I'm going to need the board space. So at this point, pause the video down, get this all written down, and then we're going to talk about the wording and what's going on in this test together. So go and pause. Okay, so let's go ahead and break this apart. Okay, so the last note I want to make about the rational zeros test is this. It actually regards into the actual kind of meat or core of the test, and that was that it made the claim, the test makes the claim that rational zeros for polynomial functions with integer coefficients take the following form: a factor of a naught divided by a factor of a n. And just to simplify notation moving forward, we're going to call this P, and we're going to call this Q. Alright, so the point I want to make is, well, first let's make sure we recall. I've already mentioned it briefly, but just to make sure we're all clear, when we're talking about A naught is the constant term from our polynomial function. Similarly, a sub n is actually on the opposite side of the spectrum. This is our leading coefficient term from our polynomial function. And just to review, let's all recall that when we say leading coefficient, this is the number that's being multiplied to the variable with the highest power. So leading coefficients. Okay, so when we are trying to determine the possible zeros, or the possible rational zeros of our polynomial function, we consider these two values. And not only do we consider these two numbers, we are going to consider the factors of these values. So take a number like 20, for example. 20 has many possible factors. So the point I want to get at is that when we are walking through this test, we are going to be producing lists of numbers because we are going to be taking all the factors of these two values. So we're going to make a list. Okay? And what's going to be important to realize is that yes, this test does help you determine what the rational zeros are of a polynomial function, and yes, it is true that the rational zeros will come from using this idea of a factor of a0 divided by a factor of a sub n. That is true as well, but we have to be very careful about is that when we're using this test, is that the key idea and the most important note probably for today's lecture is that the list we generate from these factors is the list of possible rational zeros. It is not the list of the actual rational zeros. All right, so that's the important note I'm trying to get at, is that this above line, this makes a list of possible rational zeros. All right, so that is not to say every number we're going to make using this test, that is not to say that it is actually a zero of the polynomial function. We need to determine that. All right, so, and the actual zeros must be determined by trial and error. So again, just to reiterate, when we actually use this test, all right, this core idea right here, this will produce a list of numbers for us, a list of fractions. And what we have to understand is that this list we make, while it will be the numbers we are considering to be the zeros of our polynomial function, that is not making any statement, or this test is not making any statement that these are the zeros. All right, it's just telling you, hey, if I give you a polynomial, or if you give me a polynomial function, these are the numbers I think will be zeros. I'm still leaving it up to you to figure out which ones are actually zeros. All right. So if all that wording, if all that stuff I just said was confusing you, don't worry about it. As always, we are about to do an example, and when we get our hands dirty with it, when we do the example, all this stuff will become, will make a lot more sense. So why don't we just go ahead and get right into that now. Okay, so first example, let's go ahead and consider this. Let's use our rational zeros test to identify the rational zeros for this following function. F of x equals x cubed plus 2x squared plus 2. Now, before we begin, let's make sure we understand and clarify the fact that we can actually use our rational zeros test for this function. Why is that? Well, f of x is a polynomial function. Great, there's check 1 and check 2. The a values of this f of x are all integers. Perfect. So that means we can actually use our rational zeros test. So, to actually use that test, right, it's going to be that p over q. First thing we want to do is make that p over q list. Well, that's the factors of a naught over the factors of an. So let's make sure we identify correctly what is our a naught and what is our an. Now at this point we should be able to do that with little difficulty. So give yourself a second, see if you can identify what a naught and an is. Go ahead and do so now. Alright, so hopefully we're able to see without much difficulty that a naught is 2 and an is 1. Alright, just to quickly review, a naught is always the constant term, there's our constant term 2, and is always the value being multiplied to the variable with the highest power. X cubed is the variable with the highest power, there is no number there, so there's an implicit 1. Okay, so moving on from that, the test, our rational zeros test, tells us once we identify what the a naught and an is, take all the possible factors of those two numbers. So we want all the factors of these of 2 and 1. Now, our factors of the a naught term are what we're going to call our p's, and then the q's are the factors of the an term. Just want to make sure we're clear on that notation for this test. So p's are the factors of a naughts. So we need to ask ourselves, what are all the factors of 2? Well, it's going to be 2 and 1. All right. And then for an, what are going to be the factors of 1? Well, it's going to be 1. All right. Now, here's where I want to go and take a moment, and I want you guys to think, because I'm going to tell you this right now. I have missed for both P and Q are each make a list of numbers, and for P and Q, I have missed half the numbers that are needed in those lists. So in P, I have missed 2 numbers, In Q, I have missed a single number. Okay? So go and pause the video at this point and think. What are the factors that I've missed for P and Q? Go and pause the video and think about it now. Okay, so let's think about this, all right? First off, let's understand. I said for P, I said 2 and 1 are a factor of 2. Well, why is that? That is because of the fact of when I multiply 2 and 1 together, I get 2. Now, I'm going to make the claim there are 2 other numbers out there, 2 other integer numbers, I should clarify, 2 other integer numbers that exist in which I can multiply them together and get 2 back. And they're not 2 and 1. So this is where you have to kind of do some just thinking in your head, thinking about numbers, and what way could I get 2 and 1, what way could I get 2 again through multiplication of integers. And hopefully, eventually, it doesn't matter how long it takes you, but hopefully you'd get to the point where you realize that, oh yeah, -1 times -2 is the same thing as multiplying 2 and 1 because our negatives cancel, so I also get 2. Would you look at that? And then same thing for an, right? What's the only way I can get 1 through integer multiplication? Well, our gut instinct is to say, well, just 1 and 1. That'll give us 1. What we have to remember is that if I do -1 times -1, I also get 1 back. So, what this means for us is that when we're making our list of P's and Q's, whatever positive numbers you can make for factors, so for 2, we got the positive factors of 2 and 1, there will always, always, always be a pairing of negative numbers as well. So what we need to be doing is putting a plus minus on all these factors we generate, because if the positive number is a factor, then it is guaranteed that the negative number will also be a factor, because you can just pair that negative factor with the corresponding secondary negative factor. Ooh, what I just said was really confusing. Ignore that last sentence. But yes, so big idea and an important note. So big idea and important note is that when we're making our list of factors, always pretty much whenever you identify a factor, just go ahead and write plus minus. So for all factors, write plus minus. Okay? So I've realized I've not done my board space correctly. I'm going to need that space right there. So go ahead and pause the video. Make sure you get this note written down. It is an important note. So for every example moving forward, you're going to see that I just immediately write plus factors. I just want to make sure we're clear on the idea that those I'm going to write plus minuses, and I want to make sure we're clear on the idea those plus minuses are coming from the fact that if positive 2 is a factor, negative 2 will also be guaranteed to be a factor. Okay, so I'm going to go and erase that now. So great, we have identified our P's and our Q's. Now the test tells us to go ahead and do P over Q. Do all possible combinations of P's over Q's. That's the big idea, all right? So we need to take all our P's, plus minus 2, plus minus 1, and I need to do it over all my Q's. 1, 1. I guess I should mention that I don't bother writing plus minus 2 over plus minus 1 because they'll just get both these plus minuses kind of absorb each other into a single plus minus. So you only need to write it like that. All right, so here we go. So what we can see from here is that our P's over Q's gives us a list of 4 numbers. All right, if we want to bother writing those 4 numbers out, it is 2, -2, 1, -1. There you go. So this is kind of where the rational zeros test ends. It says, this is all I can do for you. Here's the list of numbers I generated. It's now up to you to figure out which one of these are actually zeros. Okay, so we just need to, what do we have to do now? Well, we have to take these list of numbers and we just need to plug and chug. We need to figure out which one works, which one gets us that end result of being a 0. It may be 1, it may be a couple, who knows? So let's go ahead and plug these numbers in now and determine for ourselves which of these are zeros. So I'm going to go ahead and erase this portion right here, so you haven't done so already. Go and pause the video to get this copied down. Okay, so like I said, once the rational zeros test gives you that list of numbers, for now it falls upon us to go ahead and plug and chug, figure it out. So I want to do f of 2, f of minus 2, f of 1, and f of negative 1. Let's go ahead and walk through all 4 of these function evaluations. So first, f of 2, we're going to take 2 into here. So I'm going to get 2 cubed plus 2 squared plus 2. I'm going to get negative 2 cubed plus 2 times negative 2 squared plus 2. And then we're going to get 1 cubed plus 2 times 1 squared plus 2. We're going to get negative 1 cubed plus 2 times negative 1 squared plus 2. So let's evaluate all 4 of these function values. Let's do the ones first because they're easier. We're going to have 1 cubed, 1. We're going to have 1 squared times 2 plus 2 plus 2. Okay? Definitely doesn't equal 0, right? Let's try the negative 1. Negative 1 cubed is negative 1, right? Because negative 1 times negative 1, positive 1. Multiplying another negative 1 makes it back to negative 1. Negative 1 squared, that's going to be a positive 1 times 2. So we're going to have plus 2, all right? We have negative 1 plus 2 plus 2. Again, doesn't equal 0. All right, now let's try the 2 value. Okay, so we have 2 cubed plus 2 times 2 squared plus 2. Now, before we start calculating, I'm going to go ahead and take a step back and just think about it. What are we trying to do here? What is our goal right now? Well, our goal is to evaluate our function at these 4 numbers and see if it equals 0. We did 1 and negative 1 already, and we saw that it doesn't equal 0. So that already tells us that 1 and negative 1 are not rational zeros. These are not zeros for our function. Okay, so now we're about to do the 2 and negative 2. So let's keep in mind, though, that all we care about is the question is, when I plug 2 into my function, will it equal 0? All right? We don't care what number it actually equals. We just care, does it equal 0 or does it not? Now, just looking at this, I have 2 cubed. That's a positive number. I have 2 times 2 squared. That's another positive number. I'm going to be adding another 2 to that. That's another positive number. So in essence, I'm going to be adding 3 positive numbers. Will adding 3 positive numbers ever give me an end result of 0? No, it's impossible. So I already know right off the bat, I don't even need to calculate what this number is. I simply understand this is not 0, and that's all we care about. Again, all the question we're asking is, does this equal 0 or doesn't it? This does not equal 0. We don't even need to know what number it actually does equal. We can just simply understand this is adding 3 positive numbers. There's no possible way this equals 0. And why I wanted to take the time to go ahead and walk you through that and point that out is because as we'll eventually see, certain types of problems are going to give you a big list of numbers you have to check. And so whatever way you can save yourself time when checking those numbers is probably for the best. And so a big, easy way we can save time when doing a rational zero test problem is we just we can recognize the fact that we don't actually need to calculate the function value. We just need to know if it equals 0 or not. And when I plug in positive 2, I can quickly identify all I'm doing is adding a bunch of positive numbers, so it's no way it's ever going to equal 0. And I can end my check just like that and move on to the next one. Similarly for this problem, all right, I'm going to have 2 times negative 2 squared. Negative 2 squared is going to produce a positive number. 2 is also a positive number. Okay, negative 2 cubed is in fact a negative number, but we can be a bit tricky about this. We can recognize, hey, negative 2 squared is the same as 2 squared. All right? And if I multiply another 2 there, that's 2 cubed. So I have a 2 cubed basically right here, and I have a negative 2 cubed right here. These will cancel, and I'll have a positive number left over. So yet again, don't even actually need to calculate it, but I can recognize the fact that is not going to be a zero number. So I guess hopefully these little tricks I did on these two that I'm doing to save myself time make sense to you. If not, don't even worry about it. You don't even need to use my tricks. You can just simply plug and chug. That's still totally okay. Again, we're just checking, do these equal zero or not? Now then, getting back to the problem as a whole, great, we've checked the entire list. We've walked through every list, and we've determined whether they equal zero or not. And surprise, surprise, pretty interesting, none of the numbers we checked equal zero. Or when we plug them into our function, they don't equal zero. So what is that telling us? Well, that just told us then, through the definition of the rational zero test, that told us that 2, -2, 1, and -1 were the only possible rational zeros of our function, but after actually checking them, we have determined that none of them, in fact, are zeros. So what does that mean? Does that mean our function has no zeros? Well, let's think about that. I'm going to go ahead and erase this work right here, because I'm going to need some board space. So if you haven't copied this work down, go ahead and do so now. Okay, so just to review we have now reached, what the point we've reached in this example, we now understand that the rational zeros test gave us a list of possible rational zeros. That was the first thing that happened. The second thing that happened is that we checked them. We checked this list. We checked this list, but none of them worked. But none of the values work. None of the values are zeros. So after checking our list, we've determined that none of these values are actually zeros. So what does that leave us to conclude? Right? Does that mean this function has no zeros? Well, no. Right? And how can I know that pretty easily? Well, just graph that function. And if you graph that function, you will see that in fact, okay, I'm making no claim that's what the graph looks like, but I guarantee you when you graph this function, it will cross the x-axis. What does it mean to cross the x-axis? That means a zero exists. There is some value of x that when I plug it into my function, it makes my function equal zero. Right? Remember, x-intercepts are the same as zero values. Zeros are x-intercepts. So my graph has an x-intercept. Therefore, it must have a zero value. But my rational zeros test that I just used, none of the values worked. None of the values came out to be zeros. So where's the disconnect? And the answer to that question, well, go ahead and think about it for a second. Go ahead and pause the video and think about that for a second. Right? What is the zero then? Why is my rational zeros test failing, but a zero does exist? Go ahead and see if you can pause the video and give that a quick thought. Okay, so the answer to that question is just this. The disconnect that's going on here is that we did use our rational zeros test. However, every possible rational zero failed, but graphically we understand that a zero must exist because there is an x-intercept. What this means together is that the function just has an irrational zero. All right? This means the function must have an irrational zero. Okay? So just to go through one more time how we piece that together, and it's not too big of a jump, is we used our rational zeros test. We created a list of all possible, keyword there is possible, rational zeros. We tested them. How do we test them? Well, we just plug and chug. Which one of these, when I plug it into my function, actually makes it equal zero? And what we saw was none of them did. All right? So that's where we have to be a bit careful. And that's going to be a key idea about this test is, well, what does that mean for us then? And what we understood is that graphically, if I graph this function will cross the x-axis. It will have an x-intercept. So that means it must have a 0. But all my possible rational zeros don't work. Therefore, it must have an irrational 0. Whatever that number is, it's not a rational number. Okay? That's what is true about this function. And so why did I point this out? Why was the very first example I used for this rational zeros test one where it basically failed, where it didn't give us any useful information really. We still don't know what the 0 is. We just know it's some irrational number, right? And the reason why I want to do that is because we're going to be using this test for the whole lecture, and I just want to make it clear first and foremost before we start getting into it and start getting comfortable with it, is that this is a very useful test, but it is not an almighty test, if I can word it that way, right? Just because the numbers that just because this test will produce a list of numbers, and just because these numbers don't work doesn't mean we get to make statements like, therefore this function has no zeros, or just because we figure out what the rational zeros of a function are doesn't mean these are the only zeros of a function. I just want to point out and emphasize this test is only making a statement about the rational zeros of a function. It makes no claim about the irrational zeros. So we may find a function that has 20 rational zeros, but that does not mean we understand all the zeros, because it may still have one irrational zero. Or an example like this where it has no rational zeros. So through our rational zeros test, that doesn't mean we get to say this function has no zeros, because graphically we can see quite easily it does have a 0. All it means is that the 0 it has is irrational. So all I'm trying to get at is please be careful with the statements we get to make when using this test, because it can be quite easy to fall into the traps of making too broad or too powerful a statement about a function. Like, for example, this one is a great example of falling easily into the trap of making this statement, this function has no zeros, when in fact it just has no rational zeros. But besides that, let's go ahead and actually do an example where this test works and gives us information to use. Okay, so for our next example, let's go ahead and consider this following question. Let us use the rational zeros test to find the rational zeros, and then let's factor the following polynomial function. F of x equals x to the fourth plus 2x cubed plus x squared minus 4. Okay, so let's go ahead and walk through that. First, we want to understand what the rational zeros are. So, of course, we need to identify our a naughts and our an. That being 4 and positive 1. Alright? From here, we're going to make our list of p's and q's. Okay? In other words, we want to identify what are all the factors of 4 and the factors of 1. So, before we do that, I have realized I should make up certain notes. It is true that the constant term for a function is minus 4. But when I wrote the a naught, all I wrote was 4. And in actuality, it doesn't matter if I write positive or minus 4 here. And why is that? Well, when we get into making this list of p's, remember that whatever factors we make, we're automatically going to use both the positive and negative versions of those factors. And so because of that, it doesn't matter whether you use the positive or negative. It doesn't matter if I write positive 4 or negative 4 for a naughts. All right. So, and that just again, that is because for this list of p's and q's we're about to make, since we will be writing both the positive and minus versions, it doesn't matter whether I use positive or negative 4. So getting back into it, what are all the factors of 4 going to be? Well, that's going to be the list plus minus 4, plus minus 2, and plus minus 1. All right, and then what are all the factors of 1? Well, that's going to be quite simply plus minus 1. So I have my list of p's and q's. What's going to be my next step? Well, I now want to make my list of p over q's. So I want to do plus minus 4, plus minus 2, plus minus 1. I want to put this on top, or I want to make this over all the q's. So 1, 1, 1. All right. And so that's simply going to give us the list plus minus 4, plus minus 2, plus minus 1. Now, I guess I should make a quick note. For our previous two examples, this whole step of making the list of all p's over q's was kind of redundant. And why was it redundant? Because we were always just putting them over 1 each time. So each time our list of p's over q's was simply just a list of p's. So this step may seem quite redundant, and I want to make sure I emphasize that right now, is that it's only appearing that way because of the fact that our an is 1. Alright? That is the whole reason why this step right here kind of seems useless. However, when an is not 1, when an is any other value besides 1, this step actually becomes very important, and we'll see that in our next example. I just wanted to point that out right now. But regardless of that, going back to this example, we now have our list of p's over q's, and this is the point at which rational zeros test kind of stops. It's over. We've used as much, or it's done all the work it's willing to do for us, right? Because what does rational zeros test tells us? It just tells us, hey, you gave me some numbers. Using those numbers, I'm going to tell you these are your possible zeros. I'm going to leave it up to you to do the grunt work and figure out which ones are actually zeros. Right? So what is the grunt work? How do we determine if any of these numbers are actually zeros of our functions? Well, for us that just means now we got to plug and chug. So let's go ahead and do just that. So I now want to consider what is f of 4, what is f of 2, what is f of 1. Similarly, I want to figure out what is f of minus 4, f of minus 2, and f of minus 1. Okay? So, we just need to plug and chug now. So, what I want you guys to do is to go ahead and figure out from this list which of these values are going to be zeros and which aren't. Go ahead and determine for yourselves, do the calculations, find out. So pause the video, and after you unpause, I'm not going to show any of my work. I'm just going to say which values I got as being the zeros, and we'll go ahead and compare our list and see if we got the same. So go ahead and pause the video now. Okay, so hopefully you gave it a shot and figured out for yourself which of these possible values are zeros, and let's go ahead and compare at this point. So, when I went through my work, I found out that 4 was not a 0, 2 was not a 0, 1 was a 0, negative 4 was not a 0, negative 2 was a 0, and negative 1 was not a 0. So in other words, at the end of the day, I got that 1 and negative 2 are these rational zeros for our function. Alright, so hopefully we got the same answers. Excuse me. Hopefully we got the same answers. If not, go ahead and email me and we can discuss it. Though I'm pretty confident this time around that that I'm correct and that these are the rational zeros. Great. So let's go ahead and use this, alright? Because we're not quite done with the problem yet, because this problem had 2 parts. It told us to find the rational zeros, and then it wants us to factor. So let's go ahead and discuss that second portion of the problem now. I'm going to go ahead and need to erase this, so if you haven't written it already, go ahead and pause the video to get that copied down, though there isn't really much to copy. Alright. Okay, So we've finished the first half of this problem. We have identified that x equals 1 and x equals negative 2 are the rational zeros. Let me go ahead. The rational zeros for this function, for this function. Beautiful, right? So I've identified this as these 2 as being the rational zeros. However, that's only half our problem, because the second half of our problem now wants us to factor. Well, the question stands is, how do I possibly factor this 4th order polynomial? We haven't really talked about stuff like this before. We know how to factor quadratics. We use our quadratic formula. We do that box. We do our cross, so on and so forth. But how do you factor anything that's bigger than a quadratic? A 3rd order, a 4th order, a 20th order? How do we factor things like this? All right, so this is where we have to kind of recall. It's a statement we threw out either in our long division lecture or before that, but I know we made it at some point, and the statement is this. If you have a zero of a polynomial function, then you have a factor of your polynomial function. How so? Well, if x equals 1 is a zero of my polynomial function, then x minus 1, right? And if x equals negative 2 is a zero of my polynomial function, then x plus 2, both x minus 1 and x plus 2 must be factors. Must be factors of my function. Right? So we have to remember, and it's this key idea, is that there's a strong connection between the idea of having a zero of a polynomial function and understanding what a factor of the polynomial function are. There's a strong connection between those. So knowing a zero lets you know what a factor is. So knowing a zero means you know a factor. And it's a two-way street, right? If I know a factor, I know a zero. If I know a zero, I know a factor. It works both ways. So since I understand that the value x equals 1 is a zero, that automatically tells me x minus 1 must be a factor. Since I know x equals negative 2 is a zero, x plus 2 must be a factor. Great. So I've already understand what some of my factors are for this polynomial function. Okay, so let's use that. In order to use that, I'm going to need to erase this bottom portion of the board. So you haven't done so already, go and pause the video to get this copied down. Okay, so let's go ahead and use that. Okay, so remember, what does it mean to be a factor? Or at least a factor for a polynomial function. That means, to be a factor, it means that somewhere inside this big polynomial, I can break it up into smaller polynomials. In other words, f of x can be broken down into x minus 1 times x plus 2, and then times some unknown. All right, we still have portions missing. We have not factored this completely yet. But this is what I know so far, because I understand that these are guaranteed to be factors in my polynomial. Now, a quick review question is, how do I understand I have portions missing? How do I know I don't have all my information yet? I have something missing. How can I recognize that? Well, just think about the powers, right? This is a fourth order polynomial. So whatever my factors may be, when I multiply all my factors together, it should make a fourth order polynomial. Well, when I multiply these two together, all I'm going to make is a second order polynomial. So that tells me, that is how I understand I still have portions missing. So the question then to ask is, how do you determine this? How do I figure out what is missing? How do I figure out what is missing? All right. And the answer to that question is we use long division. All right. So how you determine what the other remaining portion of your factor, how do you determine what the missing portion of your factor for the function is you take the factors you do know and you long divide them with the original function. And after you do your long division, whatever is left over, that is this unknown portion. That's going to be the big idea. So how do we figure it out? Use the factors. Use the factors we know. And long divide. All right. That's what we have to do now, is we're going to use the factors we identified through the rational zeros test, And using those, we're going to do some long division, and that's going to help us produce that missing portion. So why don't we go ahead and do that now? In order to do that though, you're going to need the board space, as always. So go ahead and pause the video to get this copied down if you haven't done so already. Okay. So let's do our long division. Alright, so we're going to have two factors to use. Let's start with x minus 1. I want to take x minus 1 and I want to divide it by my original function. X to the fourth plus 2x cubed plus x squared minus 4. Now I just want to divide. Okay, so, and before we start dividing, what are we going to recognize? We're going to recognize this is a fourth order polynomial, so I need terms for every power below it. In other words, I need a cubed term, I need a squared term, and I also need an x term, but since we're missing one, I'm going to need to add in a 0x. Okay, so now we can start dividing. So, I want to match x and x to the fourth, so I need to multiply by x cubed. So I'm going to get x to the fourth minus x cubed. I'm going to write my parentheses, because it's going to help me remember that when I subtract, I need to distribute that negative. So I'm going to get a positive x cubed, so I'm going to get a 3x cubed, right? So I'm going to have 2x cubed minus x cubed. That's going to be a 3x cubed. I pull down the next term. So I want to match these two values, 3x cubed and x. That means I need to multiply by a 3x squared. 3x cubed minus 3x squared. Again, I do my subtraction, write my parentheses to help me remember to distribute. Simplify this down, I'm going to get a 4x squared, bring down my 0x. I'm going to need to multiply by a 4x to match. So I go through that process again, I get a 4x squared minus a 4x. Do my subtraction, I get a positive 4x, bring down the minus 4. And I guess I'll have to continue my work up here. So I'm going to need to multiply by a positive 4. So I get 4x minus 4 minus 4x minus 4, which is 0. Great. Okay, so went through a long division, divided by our factor, and we produced this value. Now what's important to note is that, the important thing to note is that after we did a long division, we had a remainder of 0, right? And that shouldn't be surprising. And it's actually a key check we're going to need to keep in the back of our heads, is that whenever you divide by a factor, you should get you should get a remainder of 0. There should be nothing left over, right? Factors, when divided, should always have remainder 0. So there we go. We have this portion now. Now, unfortunately, we're not quite done with our division because we've only used one of the factors, right? We still have our second factor we need to use. In other words, we need to long divide again. However, the question is, what are we going to long divide by, right? So we're not going to long divide by our original function again because we're trying to break up our original function. So we used our first factor to break up our original function into this. Then we're going to use our second factor to further break up this new function. Okay? So in other words, what I'm trying to get at, and I'm going to need to erase the board. So if you haven't done so already, go ahead and pause the video to copy my work. Okay, so what I'm trying to get at is we use that first factor to simplify down our function to this new function. X cubed plus 3x squared plus 4x plus 4. We used our original, we used one of our factors to simplify to this. Now we're going to use our second factor, x plus 2, to further simplify this new function. So we just want to do our long division again. And since this is a factor, we expect to have a remainder of 0 after we do this long division. Now for you guys, to get a chance for you to review, I want you to go ahead and pause the video now and do this long division. And after you unpause, I'm simply going to write the answer I got with none of my work. And then we'll go ahead and compare. Okay? So go ahead and pause now. All right, beautiful. So hopefully you gave it a shot. And the answer I got after I did my long division was x squared plus x plus 2. This was the answer I got. All right, so what does that mean? Well, that means that we can now understand that when we factor our original f of x, it factors into x minus 1 times x plus 2 times x squared plus x plus 2. Okay? And there it is. There's our function factored. Now, if you have a bit of an unsettling feeling about this final answer, that's okay. And I'm kind of agree with you. The reason why is, of course, when we talk about factoring a function completely, that usually means we want to factor it until it's just a bunch of linear terms being multiplied together, right? Linear terms being multiplied. This right here is a quadratic, however. So it doesn't really fit with our standard way of viewing a function that's factored completely. Ideally, we would like to split this quadratic up even further. However, we can't. This is actually this function factored completely. This quadratic can't be further factored, right? Alright, well, an obvious question to ask is why? Why can't that quadratic be factored further? And I'm going to leave that answer, figuring out that answer to you. Right? A good consider on your own question is why can't that be factored further? And the hint I'm going to give is to consider the quadratic formula. Go ahead and consider the quadratic formula and use that to kind of answer to yourself why is it that this quadratic function can't be factored further. But regardless, moving back to the question as a whole, here's our factored polynomial. How did we get there? We used that rational zeros test to identify a couple factors, and then we began to factor the function as a whole. And what we've just done is actually what we're going to come to understand is pretty much our main and only way for this class to actually effectively factor higher order polynomials is going through the exact process we just went through. So let's go ahead and write that down. Okay, so now that we have the rational zeros test as a tool we can use for this class, we can tackle this following question or ideas. How do we factor higher order polynomials? And just to make sure we're clear on it again, what do we mean by higher order? Well, for this class, higher order is any polynomial of order greater than 2. So anything that's not a quadratic or a linear function. Right? So how do we actually factor cubics, fourth orders, 20th order polynomials? Well, using the rational zeros test, we can create a process. And it's going to break down into a 5-step process. So what is it? Well, moving forward, if we ever want to factor a higher order polynomial, the first thing we're going to do is use the rational zeros test. We're going to use the rational zeros test to make that list of possible zeros. Beautiful, all right? And then what's our second step going to be? Well, you have the list of possible zeros, we still need to figure out what is an actual zero, right? So that's step 2, is plug and chug until you determine one zero. So all you need is one zero at step 1. Once you figure out one, you can stop and move on to step 3. And what step 3 is going to be is just going to be long divide. Long divide using that zero we just found. So long divide from the zero, using the zero we found from step 2. And then step 4. Step 4 is kind of a tricky one. It kind of breaks the idea this is a 5-step process, because what step 4 is repeat steps 2 and 3 until you have a quadratic. So for step 4, you want to repeat steps 2 and 3 until you have a quadratic left over. Alright, in other words, what I'm trying to get at is, say we started with a 4th order polynomial. We would use our rational zeros test. We would make our list. We could do step 2. I would find one single zero. I would divide. After I divide, I would be left with a cubic, right? We saw that in our previous example. We had a 4th order, we did one division, we had a cubic left over. So what that means in step 4 is, what I'm left over is a cubic, that's not a quadratic, so I go back to step 2. And step 2 says, go back to my list of zeros, find another zero. Okay, once I find that second zero, go to step 3, long divide again. Since I have a cubic, once I do another long division, I'll have a quadratic left over. So when I get to step 4, I have a quadratic. That's when I leave step 4 and I get to step 5. And all step 5 is use your quadratic formula to find the or I guess all step 5 is factor our quadratic in whatever way you like. For me, that basically means I'm going to use the quadratic formula. I know you guys, some of you like to use that big X or the box. Doesn't matter. But step 5 is factor the remaining quadratic. Factor the remaining quadratic if possible. Okay, and this is it. This will be our process moving forward for factoring higher order polynomials. Okay, so just to reiterate this process one last time, right? If I give you any higher order polynomial and I ask you to factor it, what that means we need to do is we start by using our rational zeros test. Use that to create that list of possible zeros. And once you have this list, you're going to enter into a looping sequence. That looping sequence is that you're going to take from your list, or you're going to plug and chug through your list until you determine one zero. Once you have that zero, you have a factor. Once you have that factor, you can long divide. After you do your long division, you're going to ask yourself, is what I have left over a quadratic? If no, go back to your list, find another zero, do long division again, ask yourself the same question. Keep on repeating that until you get to the point in which what you have left over is a quadratic. Great. At that point, you stop the looping sequence. Since we have a quadratic, we know how to find the zeros of a quadratic. We can either use the quadratic formula, which you know is what I'm going to do, or you can straight factor it if possible. We have a couple techniques to do that. Regardless of whichever one you want to do, simply find the zeros of that quadratic function. Once you find the zeros, you have the factors of that quadratic function. And then just like that, you have all the factors as a whole, and you've completely factored the polynomial function. So it may be a lot of work, and that's just kind of the name of the game when you're dealing with higher orders, just means more work, but this is the process we'll go through moving forward to factor such functions. Alright, so go ahead and take a moment now to pause and get this all written down if you haven't done so already. Okay, so let's go ahead and move on to our next example. Alright, so let's go ahead and actually walk through an example that uses this process we just defined. In other words, let's factor completely the following polynomial function. 2x cubed plus 3x squared minus 8x plus 3. Right? This is higher order. It is order greater than 2. So if I want to factor this completely, our process tells us start with the rational zeros test. Right? So in other words, let's identify what my a naughts and my an are. Alright, so should be able to identify those quickly, and that's going to be 3 and 2. Now, I want to point this out, is that our an is 2, so unlike our previous examples in which the an was 1, when we get to that p over q step, it's actually going to be a bit different. So please make sure you take note of that when we get there. But moving forward, I have a naught equals 3, so my p's are going to be all the factors of 3, which is quite simply just plus minus 3 and plus minus 1. Also for an, okay, I need to find all the factors of 2. So similarly, the factors are plus minus 2 and plus minus 1. Beautiful. So I have my A's, I have my P's and my Q's. So the next step I want to do, and this is where it's going to be a bit different from our previous two examples, is my P over Q step. I want to list all possible P's over Q's. So since that AN wasn't 1, it was 2 instead, this step's going to be a bit different from other examples, and it's going to be a bit different because what we're going to have this time is we're going to have plus minus 3 over 2, plus minus 1 over 2, and we're also going to have plus minus 3 over 1 and plus minus 1 over 1. Okay, so hopefully now with this example we can see why that P over Q step becomes much more important when that AN value isn't 1, because we get some weirder numbers with these 3 halves, and these 1/2. But regardless, moving forward, we'll simplify down because we always want the most simplified form. So we get this list of, how many numbers is that? 1, 2, 3, 4. We get this list of 8 numbers we now have to check. Ooh, baby. All right, so let's go ahead and walk through that. All right. This is step 1 of our process. We now have our list. Step 2 tells us all we need to find at this point is 1, 0. We just need to find 1. So the question is, well, how do you find 1? Well, we plug and chug, and this is kind of where you hope Lady Luck's on your side, and that the first number you choose is going to be a 0 if you have no indication. Otherwise, if Lady Luck isn't on your side, Godspeed to you. You may end up having to sit here and plug all 8 numbers in before you finally find one that works. But we're going to be a bit sneaky about it, and we're going to use the powers of having done the work beforehand, and we're going to check 1 instead, so we don't have to sit here constantly checking numbers. So if I take 1 and plug it into my function, I'm going to have 2 times 1 cubed plus 3 times 1 squared minus 8 times 1 plus 3. So that's going to be 2 plus 3 minus 8 plus 3, which is going to be 5 minus 8 plus 3, which is 8 minus 8, which is indeed 0. So look at that. We got lucky. X equals 1 is our 0. Great. So we have a 0. Now we can step into step 3 for our process, which was do some long division. So I'm going to go ahead and erase the board so to make some room for that. So if you haven't done so already, go ahead and copy the work down. I guess I should say this is step 1, this is still step 1, and here was step 2 of our process. Now we're about to move into step 3. Okay, so go ahead and pause the video now. Okay, so step 3. And step 3 is do some long division. So we had x equals 1 was a 0. That means x minus 1 is a factor. So using that, we're going to have 2x cubed plus 3x squared minus 8x plus 3. Okay, so let's go ahead and walk through this long division. Right, so I want to match the values. So I'm going to multiply by a 2x squared. So I'm going to get 2x squared minus 2x. I'm going to write my parentheses to help me remember to distribute. Do my subtractions. I'm going to get 2x squared. I'm going to get 5x squared, bring down the next value, minus 8x. Right? I want to match these values now, so I need to multiply by positive 5x. So I'm going to get 5x squared minus 5x. Do my subtraction again, remembering to distribute my negative. So I'm going to get a minus 3x. Bring down the next value, get positive 3. Go ahead and do my multiplication again. I want to multiply by a minus 3. So I get minus 3x plus 3. Do my subtraction. I get 0. Great. And remember, we do expect to get a value of 0 at the end because we are dividing by a factor. So our remainder must come out to be 0 if we did our work correctly. Wonderful. So now at this point in our process, we move into step 4. And what does step 4 tell us? See what you have left over. Is it a quadratic? If not, if it is, move to step 5. If it's not a quadratic, repeat steps 2 and 3 until you get a quadratic. Luckily for us, what we're left over with is a quadratic, so we're done with that. Now we move into step 5. So step 4, I guess we should say, we have left over is 2x squared plus 5x minus 3. This is a quadratic. Move to 5. So we have a quadratic. We can go ahead and move on to step 5 now. Okay, so again, I'm going to go ahead and erase the board, so you haven't done so already. Pause the video to get this copied down. Alright, beautiful. So now we can move into step 5. Okay, so for step 5, using the leftover quadratic we have, we simply want to factor this at this point using whatever technique we're comfortable with. Of course, for me, that means I'm going to use the quadratic formula. Right? So I'm going to get minus 5 plus or minus the square root of 5 squared minus 4 times 2 times minus 3 all over 2 times 2, which is going to equal minus 5 plus or minus the square root of 25 plus 24, all divided by 4. All right, which is going to be minus 5 plus or minus the square root of 49 divided by 4, which is going to equal minus 5 plus or minus 7 over 4, which is going to get me minus, it's going to give me positive 1 over 4, positive 2 over 4, and negative 12 over 4, which can be simplified into 1/2 and minus 3. 1/2 and minus 3. Beautiful. So there are my other zeros left over, and now I can factor my function completely. I can write my final answer, right? So remembering when we say factor completely, that means the end result we should have is ideally a bunch of linear terms multiplied together that when multiplied together make your original function. However, sometimes, like we saw with our very first example, or second example, sometimes you can be left over with a quadratic because the quadratic can't be factored. But for us, our quadratic was able to be factored. So let's go ahead and write that all together. And just before we move on to that, just so we're clear, the 0 of x equals 1/2 gives us the factor of x minus 1/2, and this gives us the factor x plus 3. So, bringing this all together, and I'm going to go ahead and erase the board now, so go ahead and pause the video to get this copied down. Alright. Wonderful. So, to bring this all together, that means this then equals x minus 1/2 times x plus 3 times x minus 1 times x plus 3 times x minus 1/2 is the complete factored form of our polynomial function. Alright, that would be the final answer. Beautiful. So we just went through that whole process we outlined before. Since for us we got lucky, we only had to do long division once. If we had to do long division again, that's no problem. We just repeat our steps until we get to that quadratic, at which point we factor that quadratic using the techniques we've already established beforehand. And there you go. To write the final answer, you simply multiply all the factors together. Or don't actually multiply them, but you get what I mean. And there you go. So there's an example of factoring a higher order polynomial completely. Let's go ahead and move on to another one. Okay, so for our next example, I'm going to go ahead and just be honest with you guys. I hate this section, and why I hate this section is going to be perfectly embodied with this following example. Alright, so let's go ahead and consider this polynomial function. f of x equals 10x cubed minus 15x squared minus 16x plus 12. All right, seems fine enough, right? And we want to factor this, let's say. No problem. We'll go ahead and do our process. So that means we need to start with our rational zeros test. Now, before we start doing that, let's take a step back and let's think a bit more conceptually. All right? What is the order of this polynomial function? Well, it's a third order polynomial function. This is a third order polynomial function, right? So how many zeros do we expect at most to see for this polynomial function? Well, third order, we expect to see at most 3 zeros. So we expect to see at most 3 zeros. Okay, that's nice to know. Now let's go ahead and walk through our process. Let's start doing the rational zeros test. Well, our A naught is 12. Right, so we need to list all possible factors of 12. So I encourage you to go ahead and pause the video at this point and see if you can come up with this list. All right, so go ahead and do so now. All right, so all possible factors of 12. The list we then generate is plus minus 12, plus minus 6, plus minus 4, plus minus 3, plus minus 2, plus minus 1. Okay, so there's our list of p's. Sure. Now let's do our an. An's 10. We now need to make the list of all factors of 10. Okay, so we need to make our list of q's. Again, go and pause the video. See if you can make that list for yourself. Wonderful. So the list we get is plus minus 10, plus minus 5, plus minus 2, plus minus 1. Wonderful. I have my list of p's and q's now. So what's my next step? Well, I need to make every possible p over q. And maybe already you can start to see why I hate this section. Well, okay, sure. I need to make every p over q. Let's go ahead and just do that. No problem. So I'm going to go ahead and erase this because I will need the room. So if you haven't had the list copy, if you don't have the list copy down, go ahead and do so now. All right. So I need to do all the p's over q's now. Sure, let's go ahead and do it. All right, so that means I'm going to have plus minus 12 over 10, plus minus 12 over 5, plus minus 12 over 2, plus minus 12 over 1. All right. I should be able to. All right. Then I'm also going to have plus minus 6 over 10, plus minus 6 over 5, plus minus 6 over 2, plus minus 6 over 1. Great. Ooh, and I already don't have enough room. All right, so gonna start over. I've already seen that I'm going to run out of room. Hopefully at this point you're beginning to see why I hate this section. All right, so let me start from top. Plus minus 12 over 10. I'm going to go a bit silent for a second. Just going to be me writing a lot. Go ahead and sit back and enjoy the show. Okay, So there it is. There's the list. Now, there's hope. That's a lot of numbers, but there's hope, right? We want these simplified. We want these fractions to be as simplified as possible, and a lot of these can be simplified. So let's go ahead and try simplifying these down, right? So 12 over 10. That can be simplified into 6 over 5. But we already have a 6 over 5. So we can cancel that out. 12 over 5 can't be simplified. 12 over 2. That can be simplified into 6. We already have a 6. So cancel that out. 6 over 10 can be simplified into 3 over 5. Which I just realized, oh my god, I missed the 3's. This list actually isn't done. Son of a bitch. Alright, so I have 3 over 10 plus minus 3 over 5 plus minus 3 over 2 plus minus 3 over 5. Okay, now the list is done. Going back into it. 6 over 10 can be simplified into 3 over 5. That's out. Can't be simplified. That simplifies into 3. That's out. Simplifies into 2 over 5. That's out. Can't be simplified. Simplifies into 2. That's out. Simplifies into 1 over 5. That's out. Can't be simplified. Simplifies into 1. That's out. 2, 1 over 10, 1 over 5. Good, good, good. Can't be simplified, can't be simplified, can't be simplified, can't be simplified. Great. So we cross some out. But that's still a lot of numbers. Alright? How many numbers is this? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 times 2, 32. There are 32 possible zeros. There are 32 possible zeros. And I want you to go back. I want you to go back and remember the first statement we made. At most, how many zeros will there actually be? 3. Out of 32, at most, we could possibly end up only using 3 of them. Alright? So, I'm actually not going to move forward with the example at all because I just don't want to bother doing this. But I just wanted to point it out to emphasize to you why I hate this section. It's because of problems like this, where it'll give you some monstrous list of possible zeros, and it just tells you good luck. Pray to the lords above that Lady Luck is on your side and that the first number you pick works, because otherwise you could spend who knows how long just sitting here plugging in 32 numbers praying that one of them works. So yes, let this be a warning to you all. This section sucks because sometimes you get problems like this. But how would you actually solve it? It's not any different from the previous example we just did. We would sit down, get ourselves ready, plug and chug, and hope we get a 0. And once we get the 0, the horror is over. We just move into our long division and we continue with our process like normal. But yet again, just wanted to point it out so you're all aware this section really does suck because sometimes you get problems like this. But with that out of the way, let's just go ahead and leave this whole thing behind and let's move on to our next topic of discussion. Okay, so for our last topic of discussion today, we're going to go ahead and introduce this idea of the intermediate value theorem. Alright, so bear with me on the wording of this theorem. It's a bit more heavy in mathematical language than other theorems we've talked about before in this class. So let's go ahead and walk through it. The theorem says this. If you have two real numbers, a and b, so if a and b are real numbers, such that a is less than b, alright? So for example, 1 and 2. Then if you have a function, f of x, and f of x is a polynomial function, such that f of a does not equal f of b. Alright, so when I plug in these two numbers, a and b, they don't equal each other. What the function outputs don't equal each other. And w is a number in between f of a and f of b. Alright, so whatever f of a and f of b may be, since they don't equal, right, there will exist a number in between them. I'm going to call that w. Then there must be at least one value c there must exist a c in the interval a comma b such that f of c equals w. All right? So that wording may be a bit confusing to understand, and that's why when you're talking about the intermediate value theorem, it is always easiest to understand it with a picture. So let's go ahead and move past that wording, and let's just consider the picture instead. So we have these two real numbers, a and b. And just like the condition states, a is clearly less than b, right? A is less than b. Okay, so when I plug a and b into my function, right, f of a and f of b, they're going to make some numbers. Don't know what. Don't know what numbers they'll make. I just know they're going to make some numbers and that they don't equal. So f of a clearly does not equal f of b. Okay. Now, in regards to the graph of this function, we know something. Since we are talking about a polynomial function, we understand that the graphs of all polynomial functions are what? There's two things we understand. We understand they're continuous, and we understand they have no sharp corners. In other words, nowhere does my function break, and nowhere do I see something like a sharp v. All right? So I have these 2 points f of a and f of b, and since I'm continuous, I know that no matter what, no matter how the line may look, right, it may look like this, right? It may look like, oh, that wouldn't be a function. It may look like this. Doesn't matter. We don't know how they connect, but we do know that these points must connect. And why do we know they connect? Because the function is continuous. So regardless of how they connect, the important point is that we know they do connect. Is that the points connect. And regardless of how they connect, right, since we are continuous, and since we have this value w, and w lies between f of a and f of b, no matter how these lines, or no matter how these points connect, at some point there will be at some point there will be a spot on the line where there exists a point that it uses the value of w. Alright? So say the lines connect like this, then the point lies right there. Let's try drawing a different line then. Right? Let's try drawing a different line. I can draw the line like that. Ooh, can't draw it like that actually. I can draw the line like this, right? Here's another way to draw the line. But still, there exists a spot, or there exists a point that uses w. Let's try drawing it a third way. I could draw it like this, right? And still there exists a point that uses w. In fact, there exists several, right? So the key idea is that, and actually I don't want to use this one, so we're going to, that is still true, but let's go back to that original one I had because it's the nicest. So the key of the idea is no matter how you connect these 2 points, no matter how you connect them, there will exist a point which uses w since the function is continuous and since w lies between f of a and f of b. So since there exists a point that uses w, correspondingly, right, because w is the y value of the point, there must also be a value for x, for the point. There must be a value c. So since I'm going to get this point, c comma w, and since this whole graph, since this line as a whole is supposed to represent my function f of x, that has to mean this tells you that f of c must equal w. Okay, so just to do a quick example using the intermediate value theorem, a lot of people call it IVT, just for the abbreviation. So like we can consider this example. By IVT, where might a 0 occur for this following function? X cubed minus x squared plus 1. Right? And so say we are given this table to represent this function, right, where we have the values, when we plug in -2, we output -11. When I plug in -1, I output -1. When I plug in 0, I output 1. When I plug in 1, I output 1. And using IVT, right, we may not know what the zero is, but through our understanding of the intermediate value theorem, we can get a good idea of where the zero must be, right? And the answer to that, the answer is that the value of x, which makes f of x equals 0, must lie in the interval it has to lie in the interval -1 to 0. Okay, and how were we able to identify that? Well, remember, we are dealing with a polynomial function. So that polynomial function, the graph of it must be continuous. So with that knowledge and using IVT, right here, we can see that our function value jumps from -1 to 1. There's a change in sign. There's a change in sign for our function. All right. If you are changing in sign, that must mean, if we're continuous, that we pass through 0 at some points, right? If I want to move from negative to positive, I have to go through 0. So by the intermediate value theorem, since 0 is in between these two values, and we want our function to equal 0, and since we want our function to equal 0, and since 0 is in between these two values because we have a change in sign, that must mean there exists a value c where c is in between the numbers -1 and 0. So if I want to figure out what the 0 is for my function, a good place to start is to look at all numbers in between -1 and 0. And so, I mean, short of that, intermediate value theorem isn't quite useful for this class. It's a good tool to kind of narrow down the search if we're trying to look for zeros. It's a good way to do that. But besides that, this class, not too much use to it. But I definitely feel like it's still worth mentioning because for all those who are calculus bound, intermediate value theorem takes a very prominent role in calculus. You do use it quite a bit there. It is very helpful and very useful to know for when you make your way to calculus. For this class, not so much, but yeah, for those of you who are calculus bound, you will definitely hear about this and talk about this again. So for that reason, I felt it was worth mentioning. Besides that, those are the only two things we're going to talk about today, the intermediate value theorem and the more important one for us being the rational zeros test, because that is the test which finally allows us to start factoring these higher order polynomials. But besides that, that's it for today's lecture. Hope everyone has a nice rest of their day, continues to stay safe, stay healthy, and I'll see you guys in the next video. See ya.